Okay, hi students. Today I want to continue the total internal refraction. That's one of the subtopic from the chapter 6, light from 4. Okay, let's see this one topic, what the intro about. Okay, first one I need to mention about the item, what we need to learn from this one topic. Okay, first one they will define the critical angle. Number 2, you need to complete the ray of the diagram. That's a refractor away from the normal. Another one is a refractor at the refractor angle. There's a 90 degrees. Then C, you need to learn about the light refracted in the glass. So when the incident angle is more than C. Okay, number 3, you need to state the two conditions where the total internal refraction can be occur. Number 4, you need to state the refractive index as related to the critical angle. Okay, last one, you need to explain about the aid of the diagram, how the light is totally internal refraction in 45 in the prism. Okay, let's see one by one. Okay, we go through to the when the incident angle is less than C. C is a critical angle. I think this one we learned before. They just are the normal refraction. Okay, we see the diagram first. The light ray is travel from the medium. Then after that go to the A. So then there should be refracted away from the normal. So incident angle is smaller, then the refractor angle become bigger. Okay, now we see the explanation. When the light travel from a denser medium, that's a water, to the less than medium means to the A, so they will bend away from a normal light. So the small part of the incident ray, they will refracted inside the water. Okay, actually they got weak of the refracted ray, they will come back to inside the water, but they're just a very small refraction. So normally we just ignore because we want to see is a refracted ray for the less than medium. So from here the angle of refraction is larger than the angle of the incident. So from here we can see the I actually is smaller, then the R is bigger. Okay, so from here I want to show about the ray, the weak refracted ray that will come back, and also I want to prove the incident angle and refracted angle, what's the relationship when I keep increasing the incident ray. Okay, let's see the diagram here. Okay, can you see when I just increasing the incident angle, the refracted angle please continue to increase. So this one we call refracted angle, this one we call incident. Okay, this one we call there's a weak refracted ray. Normally we just ignore because they're very lighter, we cannot see that exactly. So I still continue. So we repeat again, see the video. So you can see the incident they keep increase, then the refractor also continue to increase. After that you can see the weak refracted ray to come back. Okay, now we go to answer some of the question. Okay, first one they show about the diagram. The light ray is directed from the A towards to the semicircle glass block and also move out to the A. So that means the light ray is travel from the denser to the less dense. So what happened to the light when it's enter a denser medium to the less dense medium? So normally we know when they just go to less dense medium, they will refracted away from the normal. Okay, then we go to the second one. Can you compare the intensity of the refracted ray and the reflected ray? Okay, refracted ray, the first one should be this one, strong refracted ray. Then the inside, this one we call reflect, F-L-E-C ray. This one is a weak one. So now we need to compare about intensity. Intensity means the light ray. Which one is more clear, which one is a weak. So normally we see the refracted ray should be clear compared to the another refracted ray in the glass. So the answer here is refracted ray is brighter. Okay, now we need to relate incident angle and the refracted angle. From this one situation, the refracted angle will be bigger than the incident. Okay, so from here we can say about the relationship. This one question they ask about relationship, they're not comparison. If comparison, sure the I is smaller, R is bigger. Now relationship is when I increase the I, the R will keep increasing. Follow just now the experiment. Okay, now we go to prove is it the answer is correct or not. So we need to draw. So greater incident, greater refracted angle. So when you just draw the incident, so when they just come out, they will refract away. So we draw the refracted. So I keep increasing the incident angle. So you need to draw your refracted angle, also keep increasing far away from the normal. Okay, now I continue to draw another bigger incident. Okay, you can see the refracted, after that the closer with the boundary of the two medium. Okay, last one, when I just draw, I open until the incident angle is a maximum. So you find it, they become like this. So that when I just see the refracted angle become exactly at the boundary between the two medium, mean this one we call it as a refracted angle maximum. So the maximum should be 90 degrees. Okay, so from here we say the angle of refraction that approaches to the 90 degree. So this one already we call it as a maximum for refracted angle. Okay, now this one is an example. I equals C. Means when you find it there's a exactly 90 degrees, incident angle we got another name, there's a C. Okay, now we see what means of this one C. Okay, see the diagram first. Incident ray in. Okay, after that you see the refracted ray exactly at the boundary between the two medium. This one still is a weak refracted ray. Okay, now we see the explanation. When the angle of incident, okay, I keep on increasing. You're increasing the I. So the R also will keep increasing. And refracted ray will move further away from the normal. And thus they will approaches to the glass A boundary. So that means this one is a maximum when they reach the boundary. So the refracted ray, they will travel along the glass A boundary. This is the limit of the light ray. So from here already is a limit. So they can refracted in the A as the angle is cannot be any larger than 90. Okay, if they're over than 90, that means they come into the glass, then we call it another name. We cannot call it as a refraction already. So this one for refraction rate, this one is already limit for the refracted angle, that's a 90. So from here, this one angle incident in the denser medium, mean this one C. Okay, the angle you make the refracted ray exactly 90 degrees. This angle we call it as a critical angle. Okay, so from here we never say there's a I, we just straightforward call it as a critical angle. Okay, we're using the C to represent. Okay, so from here we need to go and see the refraction rate. When I create the critical angle, means R become 90. Okay, you can see they keep increasing when I just adjust the incident. So this one refracted ray, they will closer with the glass block. Okay, until the maximum. So this one we call it as a maximum already. So that means you see it exactly at the boundary. This one still is a weak refraction of the ray. So from here we call it this one as a critical angle. Okay, you can see the light ray is exactly at the boundary. That means later they will come into the glass block. Okay, this one we call it as a critical angle when the refracted angle is a 90 degrees. Okay, now we do the some of the question about critical angle. Okay, diagram 2, they show about the angle of incident increases and the angle refraction also increases. So from here we see that this one is an incident angle. Okay, this one is a refracted angle exactly 90 degrees. This one is a strong, then inside is a weak one. So from here the A, they ask you what happened to the light ray when the angle of refraction reaches to the 90. Okay, what happened for light ray? The light ray, they will exactly at the boundary here, is it? So you see the answer. Okay, refracted on the glass A boundary. So exactly the surface. Okay, B is, this is the limit of the light ray that can be refracted in the A. So the angle of incident in the denser medium means this angle. Okay, because they say the angle of the incident in the denser medium at this limit, we call it critical angle. So from here we need to define critical angle. What's the definition for critical angle? We can say about critical angle is an angle, okay, from the incident, from the denser medium, that will make the refracted angle exactly 90 degrees. So this one we call it critical angle. So from here, critical angle is an incident angle I, where the refracted angle is a 90 degrees. Okay, not everything we call it critical. Just this one situation we call it as a critical angle. Okay, now I keep increasing the incident angle. Can you see now? I keep increasing until they're bigger than critical angle. Just now it's exactly. Now it's bigger. Okay, when it's just bigger to the critical angle, that means outside at the A, we don't have any ray diagram. That means no more refraction already. Now the light ray will come in. Okay, exactly go into the denser medium. So this one we call it refracted ray. Okay, remember just now it's a weak. Now no more weak. Now it's all come in. Okay, we see the explanation. If the angle incident is increasing further, so that is a greater than the critical angle. So the light is not refracted anymore. Okay, outside is nothing really. But this one we call it as an internally refraction. That means they come into the block. So we call it internally refracted. So this one phenomena we call it as a total internal reflection. FLEC. So means all the light ray, they total to come in. Okay, never go up or come into the same medium. Okay, so from here I want to show about the how to produce a total internal refraction. Okay, so this one diagram means they already come into the glass block. When I'm just increasing the incident angle, can you see the refracted angle inside the medium? They keep increasing. Okay, so this one is an example. So when I'm just increasing, they also increasing. So this one is a situation for total internal refraction. Outside is nothing already. You cannot see any refracted ray because all the ray already is come in. Okay. Okay, now we go to answer this question about the total internal refraction. So they ask this one situation, the angle I is exceed the critical angle, means already bigger. So what happened to the light at this situation? So this one will happen is a total internal refraction. The light that will refracted in the glass. They will come into the glass. Though this one phenomena, we call it total internal refraction. Okay, now we need to state the two conditions when you want to happen total internal refraction. Okay, these two you must remember and also memorize how the total internal will happen. Okay, first one, you need to see the ray. The ray must travel from the denser to the less dense. Okay, number two, your incident angle must more than critical angle. Then total internal refraction will happen. So this one is a two condition we need to obey. Then after that, the total internal refraction can be occur. Okay, let's see the answer. Light travel from denser medium to the less dense medium. Okay, number two is angle of the incident must be larger to the angle of the critical. Okay, so from here I repeat again. The two conditions for the total internal refraction will occur. Means the first one is light ray from denser to the less dense. Number two, angle incident in the denser medium must be greater than the critical angle. So from here equation that give the relationship between the critical angle and the refracted angle. Okay, so from here refractive index we can find by using this formula. This formula actually they come from the Snell law. Okay, Snell law is a n equals sine I over sine r, is it? Okay, so that means the I must be happen in the A. So from here in the A, there's a how many? There's a come back for the 90 degrees. For the refracted angle lah. There's a 90 degrees. So sine 90. Then the sine C. C is the incident angle. We don't know how many. So normally sine 90, then we know there's a 1. So from here I can create the new formula to find the refractive index. There's a n equal 1 over sine critical angle. Okay, for example, critical angle and refractive index by using this formula. Okay, we just see the bottom, this part. Okay, n over 1 over sine c. Okay, normally you want to find 1 over n. This one, I must be happen in the incident. So from here, I put 1 over n at the bottom, means I take this one is a I. Then this one is a R. So finally, I want to find the answer just n only. If I just reverse, then you find it the n equal sine I. Sine I is how many? Sine is outside one. Outside is a 90 degrees. Then the sine C is incident angle in the medium. So this one we call it critical angle. So from here, normally the question they want to find critical angle. So from this formula, you get it is a decimal point. So if you want to find the angle, then you need to press your calculator, become sine, then -1. So this one, they will apply total internal refraction. So just now I show you, that will happen for the diamond. Because diamond inside got so many angle. After that, they will refracted the whole diamond. So that's why you can see there about the shining. Okay, so this one what we learned today. The first one is a refracted away from the normal. This one normal refraction when the angle less than C. When the angle exactly to the C, you find it refracted exactly 90 degrees at the boundary. Okay, the last one is total internal refraction. When it's just more than critical angle, all the light will go in. Okay, now we need to see the natural phenomena by using total internal refraction. Okay, first one I want to introduce is a mirage. Okay, can you see this situation? The mirage just like the long journey. Then after that, you can see the shadow on the road. This one is normally it happen during the hot day. Okay, you can see a pool of the water just on all the road. Okay, but when you just closer, then you know nothing to be seen. So let's see the example for this diagram. Okay, can you see? When it just closer, then all the shadow disappear. So this one is what I want to show. That means when starting you find it, the all pool of the water is on the surface. So that means when you drive the car, they just closer. You find it, the closer, the water shadow just like disappear. Actually, there's a shadow from the crowd. Okay, so I repeat, continue. Okay, you find it, they become clear and become clear when it just near with the shadow. Okay, so now this one is one of the questions they ask about mirage. How come the mirage will occur? So that means during the hot day, a distant route will appear as have the pool of the water that lying on the surface. When they just reach at the place, the pool of water it disappear, and actually it does not exist. So this one phenomenon we call it as a mirage. So how come mirage will happen? Then we're using what phenomena? So from here we need to explain by refer the diagram. So the first one, the light ray must travel from the sky. Okay, so from here they go through from the top to the bottom. So during the hot day, we know the hot day near the ground should be the hot A. So the A got layer. Far away from the ground, there's a cool A. Okay, cool A, you must know there's a denser. Hot A is a less than. So that means now the light is travel from the denser to less than. Denser to less than means that will bend away from the normal. So the first part here is refraction away. Second part also refracted away until certain of the angle. Okay, there will happen total internal refraction. When total internal refraction means the light that will refracted back, okay, to the cool A direction. When just refracted back, that means certain angle they will go to the observer eyes. Then the observer will see the image on the road. Okay, first one, in a hot day, a person that traveling in a car, they will see the imaginary of the pool of water that's appearing on the surface of the hot road. Okay, now we explain by one. Okay, first one, the layer of the A near the ground are hotter than, also less than. So that means I say during the hot day, near the ground must be hot A. Then the hot A, you must remember there's a less denser. Okay, now the layer is higher up are cooler and also denser. Means the cool A now is denser. So light ray now is from the sky. They travel from denser to less than. Okay, when they're denser to less than, they will refracted away from the normal. So this one normally is a process question. So we need to explain one by one. Okay, then we continue. Okay, angle of the incident, they will increasing because you refracted, is it? Angle incident increase, then the refractor also keep increase until they reach to the angle greater than the critical angle. That means what happened when the incident more than critical. So the phenomena total internal refraction will occur. So we continue. Total internal refraction occur. Now the light is refracted towards the eyes of the observer. So that means until this part X, total internal refraction happen, then the light will bend, go in. After that, they touch to the driver's seat observer eyes. That means not every angle you can see. Maybe you can see, then the driver cannot see. Okay, maybe the driver can see, but the passenger at the beside, they cannot see. So that means the angle you must exactly, okay, maybe the angle you are exactly the same, so you can see it, total internal refraction. So the last one, okay, the eye interpret the light will come from the root, not from the sky. Okay, so that means they will straightforward go to the root. Then you can see the observer, see the image of the sky as like the pool of the water appearing on the root surface. Okay, so from here you can see, okay, just like the pool of the water on the root. When you just closer, you cannot see. Why? Because your angle changes. Okay, this one is one of the video to show how come the total internal will happen for the Mirage. Okay, we see the layer of the A, normal A, warmer A. So near with the lower part is the hottest A. So hottest A, the density should be the less. Normal A is higher a little bit. Now we see how they travel. Okay, so they explain for you. Different density, this one different medium. Okay, so that means there's a straight line of the ray. But now because the layer is a different, okay, different density, so the refracted ray will happen. They continue to be away from the normal until this part. This part they will happen total internal refraction. So that means they will go to the observer eyes. Okay, then the observer eyes must be see about the straight line. So when they see about the straight line, means they can see the shadow. Okay, the shadow is on the surface of the root, or you say on the ground. So this one we call it Mirage. Okay, repeat. Okay, understand? So now we go to the next one, also same. Okay, before I start, you see the ray. Okay, the sunlight go to the object, then the object will go through the different layer of the A. So they go in the first part, refracted away, second part refracted away, third part also refracted away. So you can see the angle keep increasing. So until certain angle, that means more than critical angle, total internal will happen. So we see it. So this part still refracted. So until this angle, okay, we can find it. There's already is total internal refraction. Okay, this part is a total internal refraction. Then exactly go to the observer eyes. Then the observer can see the image. Okay, the image on the ground. So this one same like the just now. So this one can show about the clear about the refraction. Okay, until certain level they go to total internal refraction. So finally the person can be see the image. Okay, on the ground. but when they just closer, they cannot see already. So this all situation we call it as a mirage. Okay, now the second one is a rainbow. Rainbow also using total internal reflection. Now we're going to see how to explain. Okay, when the sunlight shine to the million of the water droplets in the air after the rain, a multicolor they will add can be seen. So that one is a rainbow. So how come we're using total internal reflection? Okay, now B will explain for you. When the white light from the sun, they enter the raindrops. Okay, it will refracted. So this part refracted first because different medium. After that, they will disperse into the various of the color. So now that inside the droplets, they can separate by the 7 color. Okay, after that, there will 7 color, they will component inside the raindrops. Okay, see, when dispersed color hit back, so when they just hit back in the droplets, so this undergo total internal refraction. Means inside the same medium that will happen total internal refraction. So until they want to come out, okay, before the raindrop and the air they want to come out, so they will refract again, okay, as they leave the drop. So the color of the rainbow, they run from the violet along to the lower part and also the red along the upper part. So finally you will find it that this bird becomes 7 color as a rainbow. So we start with the red color and the last one should be the violet. So this one raindrop, we're using how many phenomena? We're using 2. First is a refraction. Okay, after that inside the droplets, there is a total internal refraction. Okay, so from here, a rainbow is a colorful natural phenomena. When the sunlight that shine on a million of the water droplets in the air after rain, we see a multi-color. So this one is an example how come the rainbow will be occur. Okay, let me go to answer the question. Okay, name the phenomena which is the separation of the light into the colors arranged according to their frequency. So this one phenomena for separate the light, we call it as a dispersion. Okay, dispersion. Okay, now we need to state the 3 light phenomena produce a rainbow. First one, we know there's a dispersion because they want to separate 7 color. After that, when the air go in droplets, there's a refraction. Inside the droplets, there's a total internal refraction. So this one is a 3 phenomena. Okay, dispersion, refraction, and total internal refraction. What happened when the white light enter the raindrop? When it just enter, refraction will happen. So from here, refracted and also dispersed into the 7 color component inside the raindrops. What happened when the dispersed color hit back of the raindrop? There will happen is total internal refraction. Okay, they undergo total internal refraction. After that, what happened? Refracted again, then leave the drop. So this one is an example. The color of the rainbow from the violet along the lower part in the spectrum. After that, red is the upper part. Okay, another application, we're using the prism by using total internal refraction. This one is a periscope. So example, you see the diagram, this one is a periscope and the light is go through the prism. Okay, then after that go through the prism, normally it's a 45 degree. Then you need to know the critical angle for the prism is how many, then total internal will happen. For the prism, the angle, critical angle must be 42. That one is already fixed. If they're 42, that means your incident angle already is a 45. 45 is more than 42, so total internal refraction will occur. So we check the question. Name the component to build a periscope. So we're using what component? We're using the 2 prism, is it? Then the 2 prism must be 45 degrees. Okay, we're using 2 45 glass prism. Incident angle, that's a 45. Critical angle, 42. So that means now it's bigger. Compare incident angle and also critical. Now the incident already bigger than critical. What happened of the light ray? Enter the periscope. So that will happen is total internal refraction. Okay, now we need to draw the diagram to show the light, how to travel in the periscope. Okay, K will enter 45. After that, there will happen total internal refraction. So they will come down. L also the same. So we show the first one, the K will come down. When I hit the second prism, also is 45 degree. Then we go out again. So this one we call it second total internal refraction. We happen the first part, then go to second prism, that happen another time. So this part show about the K location. Okay, now about the L. Okay, L also the same. One part in the prism Q, second part in the prism Y. Okay, after that they go out. So this one is a L location. So this one we call total internal refraction in the periscope. Can you state the characteristic? Okay, the characteristic sure is a same size. Okay, when you want to see example for the submarine, they want to using periscope, and you see the object above the sea, normally it's the same size lah. Don't tell me you want to see the bigger one. Okay, then the second one must be upright. Okay, the man is standing, you see through the periscope also must be standing. If you're inverted, that means you don't know what is that. So we see the characteristic, virtual, upright, same size. Okay, now number 8, explain the advantages if we're using the glass prism instead by using mirror. Okay, why we using the prism is better than the mirror? Because mirror just undergo refraction. Refraction may be the light that will lost to the surrounding. But refraction for the periscope means the RAC, refraction. That means all the light is go in the medium. When they just go in the glass, that means you do not lost the light energy. Okay, so from here we just write the image is clearer. Okay, because there are no multiple images as found in a mirror periscope. Okay, mirror periscope can produce multiple images, but the prism is no. Okay, this one is a comparison for the mirror and prism. Can you see the triangle is a difference? The light just touching surface, then come down already. This one is the light totally go in the prism, then come up. So that means this one I say what's the difference? This one will lost because you can produce many multiple image from the other side. This one no. This one is a light totally go in. So from here, the mirror will not refract as efficiently as a prism because some of the light that will get refracted on the glass surface before hitting the refracted surface. Okay, the prism they will refract all the light ray because total internal refraction will be occur. So the quality of the image will be better. Okay, now we're using another application that's a binocular. They're also using the prism, but the prism arrangement is a different. So you see the first part, there's an object. Okay, red color they go in. This one we call it total internal refraction. Then they come down, second total internal refraction. Means one prism happen 2 times total internal refraction. Okay, then they come up. So the another ray also same. So can you see the image is inverted? That's a terbalik. So normally we using binocular, I don't want to see the image is inverted, is it? So normally they will put another prism. So I'm using 2 prism. Why we using 2 prism? Because we want to invert back the actual object. Okay, this one is phenomenal for the binocular. Why we using 2 prism? Using 2 prism to upright back the object. So the image now you see there's an upright. Okay, now you see state the use of the binocular. Binocular function is you want to see the distant, far away object, is it? So you're using binocular. So see the distant object. Okay, what happened to the light ray? Enter the binocular. When the light ray just enter the binocular, so there will happen is a total internal refraction. Okay, so total internal refraction that will occur. Can you state the characteristic, the final image? Sure is upright. Okay, another one is a virtual. Then your answer should be magnified because you want to see the image become bigger. So they say virtual, upright, Okay, same size. Actually, it's the same size. How come you can see it become bigger? Because you adjust the objective. Okay, the lenses, you make it become magnified. So that's why you can see it. If just through the prism, actually it's the same size. Okay, because you adjust by using the focusing. So you find it, the image become larger. Okay, now we're going to draw the light ray for the binocular prism. Okay, first one, there's a go straight in the prism. Okay, this one is a bottom light. They go in the prism, then total internal refraction, first time, second time. Then they go another prism. So another prism also will be continue. First time and second time, then they come up. Okay, now we continue at the top. Okay, the top light, first time and second time, then go to second prism. First time again, second time, then go to the last, and come up. Observer can see the image. So the image is exactly upright. The object upright, image also upright. Okay, then we go to the another application. There's a fiber optics. Okay, what are the uses for the fiber optic? Normally the fiber optic we're using for the communication. Example, for your cable. Okay, your unified cable. Another one is a medic. Medic we are using as an endoscope. Okay, so communication and also medicine. Okay, now we need to name the material of the fiber optics. Fiber optic, the material is using is a glass. Okay, then we answer number 5 first. They want you to complete the light path in the fiber optic. Fiber optic also using the total internal refraction. So that means the light ray must keep increasing inside the tube. Keep bending. How to bend? Total internal refraction. That means just bending inside only, never come out. So we draw it. Okay, the light ray go in first. Okay, then hit to the wall. Then here must be more than critical angle. Then the refractor come back. So they continuous to refractor come back. Finally they focus to the image. So this one they're using endoscope. Now we need to compare the density of the inner core and also outer cladding. Remember, total internal refraction you want to occur must be internal is a denser. Then the outside must be less than. So we know Q must be denser than the P. Okay, now we compare the refractive index. Okay, refractive index means the there's a density. Okay, the density of the P and Q related with the refractive index. For the optical density, P is less than, Q is a denser. So density higher, okay, that will make it become the refractive index also become bigger. Actually, there's a directly proportional. Means that is a more easier to be happen total internal refraction. So from here, the optical density Q higher means the refractive index also become higher. So from here, your answer is Q is bigger than the P. Okay, now we answer the 6. Explain why the light ray experiences total internal refraction when it hit to the inner wall of the optical fiber. How come total internal refraction will happen? Because your incident angle more than critical angle. Okay, now we need to give advantages for the fiber optic. Why are we using the fiber optic? So this one they will come up for the essay question. Okay, first one, they are much thinner and also lighter. So thinner and lighter, that means you're easy to carry lah. Okay, number 2, there's a large number can be sent at the one time. So that means at the one of the short time, the signal when they just send, they can send more. Okay, then after that, number 3 is just a little bit loss for the energy over the great distance. So that will save the cost lah. That means you can fulfill using all the maybe your unify is how many MAC, how many gates that will full to pass to you. Okay, D is a signal are the safe and free of the electrical interference. That means they're not related with the electrical affected. E is that can carry the data for the computer and also TV program. Okay, so this one is all is advantageous for the fiber optics. So this one is a diagram to show for the fiber optics how the light ray is travel. So this one is a total internal reflections. So our lesson just until the 6.2 total internal reflection. Then the following I will continue about that. So just thank you for your watching.